To understand our own origins, astronomers must observe star systems in their earliest stages, a chaotic period where swirling clouds of dust and gas are active workshops for building new worlds. One such system sits 433 light-years away in the constellation Aquila, surrounding a star only 5 million years old. In 1983, NASA's IRAS satellite, the first space telescope to map the entire sky in infrared, recorded a massive energy signature coming from this region. It was logged into a catalog as IRAS 19205-0746. This infrared excess occurs when dense dust clouds absorb a young star's heat and radiate it as infrared energy. While detectable, 1980s telescopes couldn't see past the host star's glare. The intense light washed out the area, hiding forming planets. Unable to resolve objects within the glare, the system remained a low-resolution anomaly for 40 years, a massive energy source waiting for telescopes with high enough resolution to see its internal structure. In 2025, the WSPT survey deployed a new generation of instruments to finally observe the environment around that young star. The team utilized the Very Large Telescope in Chile, using an instrument called SPHERE to achieve extreme high-contrast imaging. By blocking the star's light, SPHERE revealed that the dust cloud was actually a highly structured multi-ringed disk. Within those rings, astronomers identified a faint point of light, a candidate for an outer planet, now named WSPT-2b. However, bright spots in a dusty disk can be temporary clumps of material rather than solid worlds. To confirm that a planet was truly forming, the team required independent data from even more precise hardware. Confirmation came from two specialized systems, MAGAO-X in Chile and the Large Binocular Telescope Interferometer in Arizona. These instruments verified the existence of WSPT-2b at 57 astronomical units from the star. The data shows it is actively feeding, pulling matter from a local disk of gas and dust circling the planet itself. The survey also revealed a second, much larger planet, orbiting closer in at 14 astronomical units. Named WSPT-2c, it is roughly 8 to 12 times the mass of Jupiter. These two gas giants act as cosmic snowplows, clearing wide lanes through the dense material. Their gravity shapes the dust into distinct rings observed by the VLT. Rather than pushing material away, the planets pull it inward to fuel their growth. These observations capture the mechanical process of gas giants assembling themselves in real time, showing the transition from a disk of debris into a planetary system. The unresolved energy signature from 1983 now has a direct physical explanation. 40 years of technological progress have resolved the anomaly into a clear map of planetary formation. This specific system matches theoretical models of how our own solar system appeared during its youth. Watching WSPT-2b and 2c carve their lanes provides a direct look at the early lives of Jupiter and Saturn. Bridging the science gap in this field requires moving from observing raw interstellar dust to seeing that dust physically incorporated into a world. Measuring the material flowing into these planets provides the data needed to understand the exact physics of how gas giants grow. As our lenses match the requirements of our curiosity, we can now observe the universe building new worlds in real time.